All right. Nice to be here, at least remotely. Sorry I couldn't be there in person. When this meeting was first scheduled a couple of years ago, I was going to talk about something else, but some recent experiences I had with people who are becoming obsessed with the issue of whether there are trans-exponential low-minimal structures or not. I decided to talk about something else, some folklore that's apparently somewhat gotten lost. So this is going to be a fairly soft talk and somewhat similar to what Patrick was saying. Some of you might have heard this 20 to 25 years ago, but I think a lot of you haven't. So that's basically what I'm going to be doing. I see. Okay. All right. So what's the usual setup here? I'll just say a few things first. So, our bar in this case is going to go ahead and have this be the actual ordered field in the language of ordered rings. O minimal means the same thing as usual, although I'll be abbreviating it just O min because I'm writing in real time. I think I should make this a little bit thicker. So, yeah, so, all right. So exponent, so as I more or less assume everybody knows what exponentially bounded means, but let's just be sure. So if we have R as an expansion of the real field, I'm just going to say expo bounded if for each unary definable function and oops, well, I already said unary, that's okay. There exists an n and n such that ultimately, that means for all sufficiently large arguments, f of t is less than or equal to e sub n of t, where e sub n is the nth iterate of e to the x. Okay, so this is arguably one of the bigger open questions in ominimality of expansions of the reals. But it's connected with with some other things, and that's what I'm going to talk about today. And as it turns out, the fingerprints of Kobe and Sergey are kind of all over this, as well as Patrick and me and lots of other people. So I think it's appropriate for the conference. Also, a lot of young people, I've recently found out, don't know a lot of these things. And so it would be good. Normally, I think when I grew up, so to speak, you learned these things by hanging around in coffee houses and going to dinners at conferences and all these kinds of things. But for the past couple of years, as we all know, that hasn't been happening. So I might as well, so I'm going to give a talk on folklore, basically, is what's going to happen here. Okay, so with that out of the way, let's get started then. So I'm going to write some conditions down here. The order I'm going to do it in is for convenience. Let's reset it here. Okay, so first of all, here's one of the topics that's come up is, well, what if it's not true that every minimal expansion of the real field? What if it's not true that there exist any trans-exponential minimal structures? What if they're all just exponentially bounded? So here's a condition. So every min expansion of our bar is exponentially bounded. There's a condition. Now, there's another condition that is somewhat related. So we'll say every minimal expansion of our bar. Oops. Uh-oh. What's this? Sorry. I have to. Yeah, technology. I hate this stuff. I don't know. Let's see. I'll get rid of this somehow. How am I going to do this? Okay. Let's try that. So the words here, it's I use the phrase, Patrick and I use the phrase closed under asymptotic integration. And I think there are some fancier names for this around these days, but basically this does mean kind of what it says here, is that if you, for every definable unary function, there is another definable unary function that's ultimately differentiable, and its derivative is asymptotic at plus infinity to the original function. Now, let's see, here's another condition. If we have an ordered group, and this is and it's O minimal over the field. Sorry, my still not quite used to this stuff. All right, then this plus this new group is definably isomorphic to either just addition or the positive multiplicative group. Okay, so I'll just write it this way. All right, so there's another condition we have. And then finally, there's another one, no O minimal, expansion of the rational ordered group has a pole. Okay, so what's a pole? A pole is basically a bijection between a bounded and an unbounded interval, definable. So, okay, so here's a bunch of conditions, and the relation between them basically, this is the reason why I've written them this way. This implies this one, this implies this, and this implies this. So we have a chain of implications going this way. And some of these are already well documented in the literature. So this first one here, we'll do this first one here is by Patrick and I. And let's see, this was in 2002. See, so this is old stuff here. And we all worked on this. A lot of us worked on this at various points. Now, this, so exponentially bounded and O minimal, if every O minimal expansion is exponentially bounded, then every O minimal expansion of R is closed under asymptotic integration. And then if every O minimal expansion of R is closed under asymptotic integration, then we have this business of there's really no, you can't really have any unexpected definable ordered groups. That's what this says. Now, this was also documented in the same paper, but plus this is some help from Sergey on the proof of this one. And this one, so this is, well, this is folklore. So a lot of us know this. I'm going to explain, I mean, so who is this due to? I guess some combination of Sergey, me, Patrick, Kobe, I don't know. And now Alf Anschutz helped me remember some stuff or figured something out that I'd lost track of. So this is just a bunch of people. One way or another, we knew this. Now, what this has never really gotten published anywhere, of course, because first of all, it's widely believed that this assumption is false. It's widely believed that there are trans-exponential low minimal structures, although I have my days where I have my doubts on that. And on the other hand, it used to at least be widely believed that this would be true. So false implies true, not very interesting. Why would anybody publish that? Well, I think these ingredients and their relation is interesting. And so I think it's important for people to know about these things. If you're going to start playing around with trans-exponentiation, you kind of should know this stuff. If you're, oh, okay, that looks all right. Okay, good so far. Let's see if I can't hand better. Okay. Okay, on to, so let's keep track. We're gonna be working with these conditions there. So let's do a little bit of history here. So in the early days of omen and malady, question was, are there any proper minimal expansions of the rational ordered group? Okay, and there were even conjectures that this would be false. And as it turned out, there are, yes, and this was due to, sorry, this was due to Wilkie. And this was in 2005, was published anyway. That's another thing. Publication dates don't necessarily reflect when things got done, but we do the best we can. Okay, but all known examples are no poles. There's other names for this. Let's see, I think some people use semi-bounded, ultimately linear, whatever it is. But there are proper minimal expansions of the rational ordered group, but none of them define none that we know of, define bijections between bounded intervals and unbounded intervals. So with poles is still open. Now, it might seem even more unlikely than just allowing them, period. But in my experience, once this result came out, people just stopped thinking about this question in general. I mean, I seemed to talk about it, it disappeared. But this issue of whether there are pole expansions or not is interesting, as we'll see. So let's go ahead and assume one exists. And see what happens. So, all right, so let's let Q be an O minimal expansion of the rational ordered group. That defines, that has a pole. Again, that's just a definable bijection between a bounded interval and an unbounded interval. Okay, now some tricks for this have been known for a long time, that basically once you have a pole and the group structure, you can get you abstractly get something, the graph of something that looks like 1 over x. People have known how to do this for a really long time. It's pretty basic. And then, so then abstractly, you have something that looks like 1 over x, and then you have the group structure. So basically you can always map intervals to intervals. Okay, so all intervals are definably isomorphic, if you will. So we'll be using this. I could, if I have time at the end, if one want to, I can draw pictures of it. All right, we'll see here. Okay, so now we've got this thing. Okay, so a big ingredient here, which again I found out a lot of people don't know about. So there's a result of Laskowski and Steinhorn. And this was 1995. And then also, this is actually building on some earlier work of Kobe. Okay, so what we have now, then my structure Q defines some binary operations. I'm going to use these symbols such that, so we have Q less than plus and times is an Archimedean ordered field. Okay, now actually what their result was is that if your structure is not semi-linear, so in other words, if you have something, if you have a proper expansion, then basically you can find a chunk of a C2 curve, and then on there, on some interval, you can get a real closed field like this. But since we also have a pole, we can stretch it out, and we can always, and then we can take it to be globally defined. Okay, so this is just some ordered field. And we can even take the 0 for convenience, and the 1, the identity, to be 1. Okay, so these are fairly standard tricks here. Okay, so we've got this thing now. Now, on the face of it, you might think, well, wait a minute, you certainly can't have a real closed field living on, of course, it would be real closed by homonomality. You can't have such a thing that lives on the rationals, but no, of course we do. You take the set of real algebraic numbers. We have all countable dense linear orders without endpoints are isomorphic, so you just move the structure onto the rationals, and there you have such an object. So they do exist, but that's not really the point. Okay, so we've got this thing, and now we have to apply some. Now, by Sergey and I, or me, I guess I should say, and this was 1998. At least one of the following hold. I'll be lazy and stop there. So the result we basically had there is that if you are in an O minimal expansion of an ordered group, then you really can't have you can't have more than 2 non-isomorphic total ordered groups that are definable. So what this means in our case here is that either my funny addition is, I'll just use this note, is definably isomorphic to the original addition, or this is definably isomorphic to okay, so the positive multiplicative group of the field. So in other words, exponential. I see that on some people's machines, the video panel might be cutting off my writing. If that's the case, I said, oh, yes, somebody should kill the video panel. This says exponential. Okay, and then the other possibility is that Q less than plus could be definably isomorphic to the positive multiplicative group of the field. Okay, now this one certainly can't happen. Let's just talk our way through this. This can't happen because if, you know, this is that we've got this is a real closed field, and every positive element of it is supposed to have a square root. So if these are if funny plus is definably isomorphic to real plus, essentially we could pull back and get actual multiplication on the rationals, and we know we certainly can't have that in an O minimal structure because the square root of 2 is not rational. Okay, so this can't happen, and this other one can't happen either. Now, this is funny. This is one of these dangers of folklore, not writing things down. I was talking about some of this stuff to people at Fields a couple months ago now, and all I could remember was that it's really easy. I just couldn't remember the cheap trick to get it done. And Alf Anschutz, really, this has almost nothing to do with O minimality or anything else. I mean, basically, this is something about ordered rings. You can't have your positive multiplicative group be a one-dimensional multiplicative Q vector space. Why? Because 3 is not in 2 to the Q. So if you just move this statement over, this can't happen either. Okay, so what that leaves us with is that this definable real closed field, it has to be exponential. So we have it's an exponential O minimal structure as an expansion of the funny field. Okay, so what we've got now, let's write this stuff down. We'll be a little bit careful here. So I've got my structure. Oops, sorry. Don't want to stay angry. Okay, so this is, we have Q, we have less than. Here's my field. We'll have 0 and 1. I'll just go ahead and use E for the exponential that's there. And then here's the old plus, the original plus. And I don't know, whatever else might be there. We don't know what else is there. So, so now again, by Laskowski and Steinhorn, this thing embeds elementarily into an O minimal expansion of the real field. So in this language, okay, so this embeds, again, elementarily into some O minimal R. And now we're going to move things around so that funny plus goes to, this funny field structure goes to the real actual one. These guys can stay the same. This goes to e to the x. Now, I better use another symbol for this. So this goes to some new group. And then there's some other stuff here. Okay, so first of all, not only, so now we have, that's a bit ugly. Let me see if I can fix this. There we go. And so this this is an extremely useful result, and I think it's overlooked, and a lot of people don't know about this. I mean, if you're working with O minimal, if you're working with O minimal expansions of ordered groups, if you have a theory where you have an Archimedean prime model, then you might as well be working over the reals. Just, you know, so this is an extremely useful fact that I think all people should know about if they're going to play these games. Okay, but we also know, we already just showed that this guy is not definably isomorphic to plus. We just showed that up here, this is not definably isomorphic to this. So we can't, so this, in this expansion, we don't have a definable isomorphism here. So this implies, by one of these results that I mentioned earlier, that this structure R is not closed under asymptotic integration. Oh, I see. My software over here goes into a save mode and causes glitches in my writing. Interesting. And that says integration. And so now I have to be a little, let me be a little more precise than I did at first. And what the actual result of Patrick and I is that the Pfaffian closure of R is not exponentially bounded. Okay, so there we have it. If there are O minimal expansions of the rational ordered group that define, well, okay, that define unary functions from bounded sets onto unbounded sets, then there do exist trans-exponential expansions of the real field. Now, again, it's hard to trumpet this result because the conventional wisdom, I guess it's fair to say that the widely held belief is that there are trans-exponential O minimal expansions of the real field. So the conclusion is true anyway. And that there can't be O minimal expansions of the rational ordered group that have poles. So, obviously something like this, it's probably not, nobody's going to stick their neck out and try to publish something like this. But these are useful things to know, I think. And it actually indicates that of these four properties that I mentioned about, definably isomorphic groups and expansions of the rationals with poles and all these things, the question of existence of trans-exponential O minimal expansions of the real field, that's the easiest one on the face of it. Logically, that's the weakest one. So even with knowing all this technology and everything, it's still true that at least on the face of it, the easiest thing to do should be to just roll up our sleeves and exhibit a trans-exponential expansion of the real field. And I gather some people are trying to do this, and everybody has to take a crack at this at some point, I suppose. But it's also good to know that these other these other questions are at least as hard. I can say that I gave this problem of constructing an O-minimal expansion of the rational ordered group that has a pole to a highly skilled practitioner of descriptive set theory, because now everything in sight is countable. And it seemed as though, well, this is the right way to try to do some sort of forcing of descriptive set theoretic forcing to show that loads of these loads of such things should exist, and so there should be loads of trans-exponential expansions of the real field. But after this practitioner, this person claimed to have made a very, very serious attempt at it, and all the tricks, none of the tricks worked. That the usual tricks from descriptive set theory don't work. And this person's conclusion was that there just must be something extremely special about O-minimality. It is not amenable to descriptive set theory in terms of constructing things. So I think that's kind of interesting. And also, this is the I mean, I don't want to, you know, there are certain things that still belong to be shared over dinner and at coffee shops. And if you know, if any of you don't know the story of the bet between Dave Marker and Chris Laskowski about how quickly there would be proofs of the existence of trans-exponential O-minimal structures, you should find an older person to tell you about it. It's a great story. The point is, Dave won a bet, and in a sense, he still won the bet because we still don't have any examples of trans-exponential O-minimal structures. So, all right. So there's one other thing I want to mention here, because we can go a little bit better here. This Pfaffian closure of R. This is, you know, construction. In this generality, it's due to Speisiger. We know that you can always start with an O-minimal structure and go to this big thing where you close off under certain kinds of solutions to integral manifolds and this kind of stuff. We don't have to go quite that far to get something that's not exponentially bounded. And I think this is an interesting thing to know as well. Let me briefly explain that too. This is a result of Kobe, Sergey, and Patrick. And this is also, I was surprised by the number of people who don't know about this, but maybe my surprise, maybe there are explanations for that. This was published in 2000. And this is basically that O-minimality is always preserved under expanding by multiplication. And this over expansions, I should say, over expansions of the real additive group. Okay, so if you have an O-minimal expansion of the real additive group, and that's all you know, you can always expand by multiplication, and you preserve O-minimality. So this is a nice result. The problem is, it appeared in a conference proceedings. It was a logic colloquium one, I believe. And it was on that cuspy part, the end of the 20th century, where none of this stuff's not online. I mean, if you go to MassSciNet and go look for this paper, you'll find the reference for it, but there's no download. You can't, it's a book. You have to get the book somehow, or you have to get the paper from one of the authors or a library. So that might account for why so few people know about it. At least in my experience, not that many people know about it. But what's interesting there is that as part of the proof, has to do with this question about definable groups. So the result here is that so going back to, remember, we have our funny R star here. This was and this is not definably isomorphic to plus. This was back in my structure R, but it turns out that there always is an isomorphism. Actually, I guess the way to go about that is let's see, somehow we know that ordered groups definable in O-minimal structures are Lie groups, and so there has to be an abstract isomorphism, but it turns out these abstract isomorphisms have to be definable in the Pfaffian closure. But there is an isomorphism, well, let's just call it phi, such that R phi is O-minimal. Now this isn't true. This is true for any O-minimal expansion of the field of reals. So you might have a definable global group in there that's not definably isomorphic to either plus or times, but once you can add an isomorphism, and then it is. But we can also show by other arguments that in this case, because this is not, then it turns out that this guy here is not exponentially bounded. Now, it's just a nice thing to know. I mean, it actually uses the Pfaffian closure technology. This isomorphism, they're all, and any of these isomorphisms, they're all going to be definable in the Pfaffian closure, but on the face of it, this is a much smaller structure than the whole Pfaffian closure itself, and rounds out nicely this whole issue of the connection with definable groups. Oh, there is some documentation of this argument. But it also has to count as folklore because it's also unpublished. See my web page for a note on this. So it's somewhat documented, but it's still folklore. It's called the two-group question or something. So, okay, the details of this are known, and that's something that that can be checked. Again, just never found any particular reason to publish it. So, I mean, I think it's an interesting question, and if we're going to keep dealing with, I don't know, resurgent COVID epidemics and various things like that, if we're not all meeting in person and hanging out and talking about things, it's going to be a lot more difficult for younger people to learn these oddball, this folklore stuff. And maybe we should all be thinking about, I don't know, ways to get around that. But hopefully we don't have to, but it might be something that we do have to. Okay, so let me just, there's one other thing I'm going to mention here. So let's just look at a concrete case of something here, in case somebody wants to try to cut their teeth on something. So let's go ahead, let's let P, let's say, be the prime submodel of the real exponential field. Okay, so now by argument I kind of mentioned already, whoops. Well, we have a nice countable dense linear order here. So we know that this is isomorphic to Q less than, abstractly. So let's move the structure, push P onto Q less than. So right there, all right, so now we have an exponential O minimal expansion on the rationals. Okay, so now the question is the expansion by actual plus O minimal? Well, if it is, by arguments that we've just gone through, there are trans-exponential O minimal structures, because you could then use Laskowski and Steinhorn again to pull it back, say that you're still in, I don't even know if it's really more that you just repeat some of the arguments of the proof, but you pull this back, you get a funny group now that's not definably isomorphic to something, and then once again we get trans-exponential structures. Now, I don't know, maybe it's possible to just outright prove that that it isn't, that this one fails, but this is still open as far as I know. And it's just an indication of, you know, how much maybe we don't know as far as I know. So I'd be interested to know if anybody knew how to do this. I don't know how to do it offhand, but I haven't really thought about it very hard. So there's something to play around with if you're interested in these kinds of things. So I think with that, I'm going to end, and yeah, I'll leave it at that for now. Thanks.